Tonight, we're going to explore something that sounds alarming at first, but is actually one of the most exciting developments in modern science. Astronomy, one of the oldest, most disciplined fields of human knowledge, is facing a crisis. Not a small one, not a minor adjustment, a crisis big enough to shake the foundations of our understanding of the universe. You've probably heard scientists talk about dark matter, dark energy, the Big Bang, or the expansion of the cosmos. These ideas form the core of the standard cosmological model. But here's the part most people never hear. The deeper we look, the more the universe refuses to follow that model. Massive structures that shouldn't exist, galaxies too mature too early, expansion rates that refuse to agree with each other, observations that don't line up even when the data is perfect. It's as if the universe is holding up a mirror and saying, "Your story is close, but not quite right." And once you truly understand what these contradictions mean, what they imply for physics, cosmology, and our picture of reality, it changes the way you see everything. Because this isn't a crisis of failure, it's a crisis of opportunity. A moment very much like the time astronomers discovered Neptune by predicting a missing planet, or the moment Einstein rewrote our understanding of gravity. Every major leap in science begins at the edge of confusion, at the moment when the universe stops obeying the rules we expected it to. Before we dive deeper, if you enjoy this kind of mind-stretching exploration of cosmic mysteries, a quick like or subscribe really helps the channel grow. It's such a small thing on your end, but it genuinely pushes these videos to more curious minds. Thank you. Now let's dive in. Let's begin at the point where the contradictions started forming. Subtle anomalies that over time grew into something impossible to ignore. For more than a century, cosmology has been anchored by a model that felt unshakable. The universe began in a hot, dense state. It expanded, cooled, formed stars, built galaxies, and eventually evolved into the cosmic web we see today. Countless observations supported this narrative: the cosmic microwave background, the distribution of galaxies, the abundances of the elements, and the accelerating expansion of space. Every new telescope seemed to reinforce the story. But beneath that sense of confidence, something quieter was brewing, subtle discrepancies that would later become impossible to ignore. At first, the universe's misbehavior felt like numerical noise. A galaxy too bright here, a cluster too dense there. Nothing dramatic enough to break the model, but just strange enough to provoke long meetings and cautious papers. Then came the deep field images, snapshots of the earliest eras of the cosmos captured with clarity no one had ever achieved before. Suddenly, astronomers were staring at galaxies that shouldn't exist, systems too massive, too structured, too evolved for how young the universe was at that time. Instead of the expected population of small, chaotic, early proto-galaxies, the cosmos was showing something far more mature, something that defied everything the timeline said should be possible. As more of these anomalies piled up, the tension in the data grew louder. The calculations did not align with the predictions. The story we told about the early universe, its speed, its structure, its evolution, no longer fit what telescopes were revealing. And the more precise the observations became, the more the universe seemed to drift away from the neat, orderly framework cosmologists had built. It wasn't a sudden collapse. It was a slow, steady unraveling, a kind of cosmic whisper saying, "Look again." And so modern astronomy found itself standing at an unexpected crossroads, not because the universe broke the rules, but because the rules may never have been complete. The moment the James Webb Space Telescope began returning images, the crisis accelerated. Webb was designed to peer deeper into time than any instrument before it, back to the first few 100 million years after the Big Bang. What astronomers expected to see were small, faint embryonic galaxies just beginning to form. What they actually saw were giant, brilliant systems bursting with stars and heavy elements, structures that should have required billions of years to assemble. It was like discovering skyscrapers in a world where you expected tents. These observations were not outliers. They were everywhere Webb looked. Massive galaxies sitting impossibly close to the dawn of time, stars that seemed too old for the age of the universe at their locations, chemical signatures that required multiple generations of stellar evolution, even though not enough time had passed for those generations to occur. The early universe was supposed to be a chaotic fog, dimly lit by the first small unstable stars. Instead, it was vibrant, organized, shockingly mature. Something was deeply wrong. And this wasn't the only wound in the model. Elsewhere, telescopes measuring the expansion of the universe were producing numbers that refused to agree. Local measurements, using exploding stars and pulsating variables, painted a picture of a faster expansion. Meanwhile, measurements tied to the early universe suggested something slower. Both methods were sound, both experiments were precise. And yet they diverged so sharply that cosmologists had no choice but to confront the possibility that a pillar of their model, the very rate at which the universe expands, might not be understood at all. Meanwhile, vast cosmic structures revealed by radio surveys challenged another foundational assumption: the idea that the universe looks roughly the same in every direction on very large scales. Instead, astronomers found gigantic walls and filaments stretching across space in patterns so vast they bordered on violating the physical limits of what could have formed in the time available. The telescopes weren't failing. They were succeeding so well that they forced a reckoning. They showed us a universe that had outgrown the story we'd written for it. Among all the anomalies shaking modern cosmology, none are as striking or as unsettling as the galaxies forming far earlier than they have any right to. These are not faint smudges of light or primitive clusters of stars. They are vast, luminous, complex systems filled with heavy elements, swirling disks, and star populations that suggest long cycles of birth and renewal. And yet, by all our calculations, they appeared at a time when the universe should still have been in its infancy. To understand why this is such a problem, imagine trying to read a book and finding entire chapters written long before they should have existed. That is what these galaxies represent. According to the Standard Model, the universe needed hundreds of millions of years just to form the first stable stars, and much longer than that to create enough heavy elements to build complex structures. But these early galaxies tell a different story, one where the universe raced through its developmental phases with impossible speed, assembling enormous systems nearly as soon as the cosmic lights came on. Some of these galaxies contain elements like carbon, oxygen, and iron, in quantities that require multiple generations of supernovae. But those generations require time, far more time than exists between the Big Bang and the moment these galaxies appear. Their masses are staggering, rivaling or surpassing the size of the Milky Way at a point in cosmic history when such behemoths should have been unthinkable. Simulations strain to reproduce them, models fail, explanations multiply, each one stretching the boundaries of known physics. Perhaps star formation was far more efficient in the early universe than we believed. Perhaps dark matter clumped more aggressively. Perhaps the laws of gravity behaved differently under extreme conditions. Or perhaps, in the most radical interpretation, our timeline of the early cosmos is simply incomplete. These galaxies shouldn't exist, and yet they do. And because they do, they stand as monuments to a universe that refuses to be confined by our expectations. They are not errors in observation. They are challenges, daring us to rethink what we thought we knew about how everything began. If there is one problem in modern cosmology that refuses to fade into the background, it is the conflict over the expansion rate of the universe. For decades, astronomers believed they had finally pinned down this elusive number, the Hubble constant, a value describing how fast space itself stretches over time. But as measurements improved, confidence did not grow. Instead, something far stranger happened. The universe began giving two incompatible answers. One method looks to the nearby cosmos. By observing Cepheid variables, supernovae, and other reliable standard candles, astronomers calculate how fast galaxies around us are receding. These local measurements consistently point to a faster rate of expansion. Another method reaches deeper into time, studying the cosmic microwave background, the ancient afterglow of the Big Bang. That relic light carries information about the early universe's density, temperature, and structure. From it, cosmologists infer a different expansion rate, slower, more measured, and fundamentally at odds with the local value. These aren't sloppy measurements or outdated techniques. They are the most precise observations ever made, backed by decades of refinement, and yet their conclusions diverge in a way that should be statistically impossible. It's as though the universe is offering two narratives of its history, each internally consistent, but mutually incompatible. Some scientists argue that new physics may be needed, something that changes the behavior of dark energy or alters the laws of early universe expansion. Others speculate that unknown particles or fields could have influenced cosmic evolution in ways we've never considered. Still others suggest our entire framework for interpreting the cosmic microwave background may require re-evaluation. What's clear is this: the expansion disconnect is not going away. Every year, new measurements push the tension higher. Every attempt to reconcile the numbers with the standard model only creates more questions. The deeper we look, the more the universe seems to assert that something fundamental in our understanding is missing. This disagreement isn't a crack, it's a fault line, one running straight through the foundation of cosmology. While the expansion crisis was brewing, another mystery emerged from an entirely different corner of astronomy. Radio surveys and galaxy mapping missions began revealing structures so enormous that they defied the limits of what should be possible within the lifetime of the universe. These weren't small quirks or statistical outliers. They were colossal formations, superclusters, filaments, and voids, spanning billions of light-years in size. Patterns stretched across cosmic distances so vast that they seemed to violate one of the most cherished assumptions in cosmology, that the universe is homogeneous and uniform on the largest scales. According to the standard model, the cosmic web should only grow so large, constrained by the amount of time gravity has had to pull matter together since the Big Bang. But some of the formations we've observed exceed that threshold by staggering margins. They are too long, too connected, too coherent. They imply that gravity had help, or that it operated under conditions far more efficient than our theories predict. Just as troubling is the distribution of these structures. They appear in orientations and alignments that are difficult to explain as random. Some seem to follow patterns that hint at influences stretching across epochs, as though the early universe carried imprints of processes far more complex than expected. The existence of these superstructures forces cosmologists to confront uncomfortable possibilities. Perhaps dark matter behaves differently on the largest scales. Perhaps the initial conditions of the cosmos were not as uniform as the standard model assumes. Or perhaps the universe evolved in phases, periods of accelerated clustering or exotic physics that left behind scars in the cosmic web. Whatever the explanation, these structures stand as monuments to a universe that refuses to fit neatly into the boxes we have built for it. They push against the boundaries of our models, demanding a broader perspective, one that acknowledges that the cosmos is capable of building things on scales we never considered. The universe, it seems, is larger and stranger than our theories ever anticipated. One of the great surprises of the modern era of astronomy is not the universe's chaos, it's its order. For decades, cosmologists believed that the early universe was a turbulent place, filled with small, irregular clumps of matter that would eventually merge into galaxies. Everything was expected to be messy, uneven, and primitive, but observations tell a different story. The universe's earliest structures show a level of smoothness and organization that defies the predictions of the standard model. Instead of broken fragments assembling slowly into larger systems, many early galaxies appear coherent, stable, and even elegant. Their symmetry, their rotation, and their distribution challenge the idea that the early cosmos was dominated by violent, chaotic processes. It is as if structure emerged with unnatural efficiency, as though the universe had a head start it should not have had. Even more troubling is the uniformity observed across vast regions of space. Temperature measurements from the cosmic microwave background reveal a cosmos that is far more even than should be physically possible given the short time light had to travel across early space. This horizon problem, a cornerstone of the cosmology crisis, suggests that parts of the early universe that should never have interacted somehow ended up sharing an almost identical temperature. Inflation theory was introduced to explain this extraordinary smoothness, proposing a brief moment of exponential expansion in the early universe. But even inflation, once the hero of cosmology, is beginning to show signs of strain. As new observations roll in, the simplicity of inflation gives way to a tangle of competing models and theoretical complications. Some physicists now argue that inflation may not be the full story, or that it may hide deeper mysteries we're still unable to grasp. The consistency of early cosmic structure, paired with the unexpected sophistication of early galaxies, suggests that something fundamental shaped the universe's growth in a way we do not yet understand. It forces us to reconsider what early truly means, and whether our picture of the universe's first moments is as complete as we once believed. In the symmetry we find contradiction, in the order we find crisis, and in the crisis we find the first glimmers of a new understanding waiting just beyond our reach. For decades, dark matter and dark energy were seen as the elegant solutions to astronomy's biggest mysteries. They accounted for missing mass, explained the accelerated expansion of the universe, and tied the standard cosmological model together with mathematical precision. These unseen components made up 95% of the universe, and though invisible, they provided the scaffolding that allowed galaxies to form and space itself to stretch. But as new data pours in, even these once reliable pillars have begun to show cracks. Their behavior, once thought to be predictable, now appears to be far more complex and possibly far stranger than we assumed. Dark matter, for instance, does not always distribute itself as theories predict. In some galaxies, stars move as if dark matter is overwhelmingly dominant. In others, it seems to vanish almost entirely. Certain dwarf galaxies exhibit internal dynamics so bizarre that they appear to challenge the very concept of dark matter halos. And then there are galaxy clusters where dark matter appears offset from visible matter in ways that defy traditional interpretations. These inconsistencies suggest that dark matter may not behave universally, that it may interact, clump, or evolve under conditions we do not yet understand. Dark energy is no less perplexing. It was introduced to explain the observed acceleration of the universe's expansion, but new measurements hint that the acceleration may not be constant. It may vary, it may evolve, it may not fit the simple equation cosmologists once believed it did. If dark energy changes with time, then our entire understanding of cosmic evolution, past, present, and future, may require rewriting. The smooth, predictable picture of expansion becomes a far more dynamic, uncertain phenomenon, one that may be influenced by unknown fields or forces. Worse yet, dark matter and dark energy remain completely undetected in laboratory experiments. Decades of effort have revealed nothing. No particles, no signatures, no interactions beyond gravity. It is as if 95% of the universe is made of something that refuses to reveal itself in any way we can measure directly. And while this does not disprove their existence, it reminds us that the concepts we lean on so heavily may be placeholders, temporary frameworks waiting for deeper explanations. These invisible uncertainties highlight a truth that is becoming impossible to deny. The universe is not only stranger than we imagined, but potentially stranger than our models even allow. Dark matter and dark energy may be clues, not conclusions, signposts pointing toward a deeper layer of physics that has yet to emerge. Gravity has been the most reliable force in physics since the days of Newton. It shapes planets, builds stars, sculpts galaxies, and governs the evolution of the universe. Einstein's general relativity refined it into one of the most beautiful theories in science, a framework so precise that it predicts the bending of starlight, the rippling of space-time, and the choreography of black holes with uncanny accuracy. But as astronomers push gravity to its limits, testing it across cosmic distances, Signs are emerging that even this mighty theory may not tell the full story. On galactic scales, the motions of stars often defy expectations. The outer edges of galaxies rotate faster than they should, even after accounting for dark matter. Some systems show gravitational behavior that differs wildly from others of similar mass. The delicate structure of galaxy clusters reveals tensions that standard gravity struggles to resolve, and the early universe presents an even deeper challenge. Galaxies appear to have formed and grown more quickly than gravity should allow. These anomalies raise a profound possibility that gravity itself may behave differently on the largest scales. Some physicists propose that general relativity, though exquisitely accurate locally, may require modification when applied to the cosmos. Others suggest that gravity might be emergent, shaped by deeper unknown principles. There are theories where gravity weakens or strengthens depending on the density of the environment. Others imagine that space and time themselves are woven from quantum structures that create gravitational effects we have not yet learned to predict. The idea of modifying gravity is not new, but what is new is the accumulating evidence that something may indeed be missing. Not because Einstein was wrong, Einstein was almost certainly right within the realms he tested, but because the universe is forcing us to extend his ideas into territories he never imagined. Just as Newton's laws were not discarded but expanded, our understanding of gravity may now stand at the threshold of a similar transformation. When gravity misbehaves, it is not chaos, it is an invitation. An invitation to explore deeper laws, to uncover hidden mechanics, and to confront the possibility that the cosmos operates under principles that transcend our current theories. And every anomaly we observe is a reminder that the universe is not limited by our expectations. Every major scientific revolution begins with a moment when the impossible becomes real. Planets orbiting other stars were once dismissed as fantasy, until the first detection shattered centuries of certainty. The expansion of the universe was unthinkable, until observations forced us to accept it. Black holes were mathematical curiosities, until they emerged from theory into reality. Today, astronomy stands at another such moment, one in which phenomena once deemed impossible are appearing with increasing frequency, demanding explanations that our current models cannot provide. Some of the earliest galaxies we observe possess masses that rival the most mature systems today, yet they formed only a blink after the Big Bang. Enormous cosmic structures stretch across distances that seem to violate the maximum size allowed by the standard model. Stars appear older than the universe should allow at their location in time. Even the cosmic microwave background, long considered the triumph of the Big Bang, contains subtle anomalies that do not fit neatly within the accepted framework. One by one, these impossible findings accumulate, not as isolated accidents but as a pattern that whispers the same truth. The universe may be governed by physics we have not yet discovered, and while this may seem unsettling, history shows that such moments are the catalysts for progress. Before Neptune was found, the motions of Uranus didn't make sense. Before relativity, Mercury's orbit broke the rules. Before quantum mechanics, atoms misbehaved. Today's anomalies are tomorrow's breakthroughs. The impossible is not the enemy of science, it is the engine that drives it. Each contradiction is a signpost pointing toward a deeper layer of reality, waiting to be uncovered. And if the universe seems to be breaking its own rules, it may be because those rules were never as complete as we believed. This is the quiet, exhilarating truth hidden beneath the crisis. We are living in a moment when the cosmos is beginning to reveal more of itself, and the discoveries still ahead may reshape our understanding of existence in ways as profound as any revolution in the history of science. What we are witnessing today in cosmology, the contradictions, the tension, the unease, is not unprecedented. Science has faced crises before, moments when observations refused to align with accepted theory, and the entire structure of knowledge seemed to wobble. In each case, these moments were not failures. They were turning points. They were the prelude to breakthroughs that reshaped our understanding of the world. In the early 19th century, astronomers noticed that Uranus did not follow the orbit predicted by Newtonian mechanics. Something was wrong. Newton's laws had seemed absolute, but the data did not lie. Instead of abandoning the theory, astronomers looked deeper and discovered Neptune, a planet whose gravity explained the anomaly. A crisis in orbital mechanics became a triumph of predictive science. Centuries later, Mercury's orbit presented another problem. Its precession deviated from Newton's equations by a tiny but unmistakable amount. Again, the discrepancy lingered like an itch no one could scratch. Only with the arrival of Einstein's general relativity did the mystery resolve. The crisis was not a failure of Newton, but a window into deeper physics. Newton's laws had been right within their domain, but the universe extended beyond that domain. Even the Big Bang model itself was born from chaos. When Edwin Hubble discovered the expansion of the universe, the idea contradicted the steady-state model favored by many astronomers. The crisis forced a rethink, and that rethink gave birth to modern cosmology as we know it. These historical parallels matter because they remind us that scientific revolutions begin with discomfort. They emerge from confusion, contradiction, and friction between theory and observation. Today's cosmological anomalies are not signs that science is broken. They are signs that science is working exactly as it should. The universe is revealing new layers of itself, and in doing so, it is forcing us to let go of old assumptions. Every puzzle is a doorway, every contradiction is a clue, and every crisis is a sign that a deeper truth is waiting to be found. As the discrepancies mount, cosmologists find themselves facing a profound decision. They can tighten the existing framework, adjust the parameters, refine the models, add new components to patch the gaps, or they can entertain a more radical possibility, that the universe is preparing to reveal a new paradigm, one as transformative as relativity or quantum mechanics. It is not the data that is fragile, it is our interpretation of it. The standard model of cosmology succeeded because it was elegant and powerful. It described the overall structure of the universe with impressive accuracy. But elegance alone is not truth. And when observations repeatedly challenge elegance, it becomes clear that the model's beauty may be hiding deeper complexity. Perhaps dark matter is not a single particle, but a spectrum of unknown phenomena. Perhaps dark energy is not a constant, but a dynamic field that evolves over time. Perhaps gravity emerges from quantum processes we cannot yet describe. Or perhaps entire chapters of cosmic history, epochs of accelerated growth, phases of enhanced structure formation, remain undiscovered. What matters is this: the universe is not wrong. Our story is. And that is not discouraging, it is electrifying. The questions that cosmology struggles with today are the same kinds of questions that once led to the discovery of black holes, the nature of space-time, and the origin of the elements. We are standing at a frontier, and frontiers are always marked by uncertainty. They are the boundary between what we know and what lies beyond. Astronomy is not in crisis because it is failing. It is in crisis because it is evolving, because new data is forcing growth, because the universe is bigger, older, younger, faster, slower, smoother, rougher, and more surprising than the models we built to describe it. This is not the end of our understanding. It is the moment right before everything changes. A reinvention is coming. Whether it arrives in the form of new particles, new physics, or a new interpretation of cosmic history, its arrival is inevitable. The universe is pushing us toward it with every anomaly we uncover. As the evidence accumulates and the contradictions deepen, one truth becomes clearer than ever. We stand on the threshold of a new era in cosmology. The universe is speaking, not in whispers, but in patterns, patterns etched into the light of distant galaxies, woven into the texture of the cosmic microwave background, encoded in the distribution of matter across billions of light years. These patterns do not conform to our expectations, but they do not need to. The universe is under no obligation to remain simple, simply because simplicity comforts us. The crisis facing modern astronomy is not an ending. It is a beginning. It marks the moment when our current understanding has reached its limits. Beyond those limits lies an expanse of new physics waiting to be discovered. It is possible that we are standing where humanity once stood before Newton, before Einstein, before the quantum revolution, on the precipice of a transformation so profound that future generations will look back and marvel that we ever thought the cosmos could be contained within the equations we now use. Already young researchers are proposing bold ideas. New missions are being designed to probe the expansion rate, search for dark matter signatures, and map cosmic structure with greater precision than ever before. Theoretical physicists are exploring models that challenge long-held assumptions about space-time, gravity, and cosmic evolution. And amidst this frenzy of exploration, one certainty emerges: whatever comes next will redefine our understanding of existence. The universe has stopped obeying the story we wrote for it. But that does not mean it is breaking the rules. It means it is revealing the deeper rules we have not yet learned. Every anomaly, every contradiction, every impossible galaxy and oversized structure is part of that revelation. They are not signs of failure. They are signs of dawn, the dawn of a new cosmic story that will reshape everything we believe about the origin, evolution, and fate of the universe. And when that story is finally written, its first chapter will begin here, with the moment when astronomy faced a crisis and, instead of collapsing, used it as a bridge into a richer, more astonishing understanding of reality.